Okay, so here we're picking up with the second part of our lecture on cache memory, and today we'll be discussing some of the cache memory principles and characterizations of cache memory. So if you have the 11th edition of the book, this is chapter 5, but it's chapter 4 in the 10th edition, and I'm not sure in the 9th edition or previous editions. So our cache memory is designed to combine the memory access time of expensive high-speed memory that are near the registers, combined with large memory size of less expensive lower memory, which are, like in your RAM. The cache contains a copy of the portions of that main memory. So we move things from the main memory to the cache. So when the processor attempts to read a word from memory, it makes a check to determine if the word's in the cache. If it is, then we deliver it to the processor. If not, then we need to read in a block of main memory into the cache and then deliver that word to the processor. So there are a couple terms. One is the block, which is the minimum unit of transfer between the cache and the main memory. And then a frame is the data transferred and the chunk of physical memory. The term frame or block frame is sometimes used with references to the caches. So there you can see the cache and the main memory, and we're transferring those blocks between the main memory and the cache. Other terms, line, which is a portion of cache memory capable of holding one block, and that's usually called because we draw it as a horizontal object. They also have control bits to let us know which block of main memory that corresponds to. And the line size, which is number of data bytes or block size that's contained in line. And the number of lines needs to be less than the number of main memory blocks. So main memory consists of 2 to the n addressable words, with each word having a unique n-bit address. For mapping purposes, the memory is considered to consist of a number of fixed length blocks of k words each, so that the m equals 2 to the n divided by k blocks in memory. The cache will consist of m lines, which each line contains k words plus a tag, and also contains control bits such as a bit to indicate whether it's been modified since it was loaded in the cache. If it gets modified while it's in the cache, we have to modify it back out to main memory. The length of the line, not including the tag and the control bits, is the line size. So the term line size refers to the number of data bytes or block size contained in line. It can be as small as 32 bits, with each word being a single byte. In this case, the line size is 4 bytes when we're looking at the example in the book. And then tag is a portion that is used for addressing purposes. So here's the overall process. We start and then we receive a address read request from the CPU. If the block containing that read request is in the cache, then we fetch it from the cache and deliver it to the CPU. Otherwise, we need to go out to main memory for the block of memory containing the read access, allocate cache line for the main memory block, load that main memory block into the cache line, and then at the same time deliver that word to the CPU. This is figure 4.5 on page 130 of the text, in case you're reading along in the text. So there are a number of different characterizations or elements of cache design. And in this section, there are occasional references to high performance computing that deals with supercomputers and their software, especially for scientific applications that involve large amounts of data, vector or matrix computation, and the use of parallel algorithms, which if you started early on 7 million humans, you've seen some of the parallel processing strategies that can come into play. So the different elements are the addresses, the size, mapping functions, replacement algorithms, write policy, line size, and number of caches. And let's go through each one of those. So the cache address in virtual memory is a facility that allows programs to address memory from a logical point of view without regard to the amount of main memory that's physically available in terms of virtual memory. When used with virtual memory, the address fields of the instructions contain the virtual addresses. For reads to and writes from the main memory, a hardware memory management unit translates each virtual address into a physical address in the main memory. So there can be a physical and a logical cache. A logical cache or virtual cache stores data using virtual addresses. The physical cache stores data using the main memory physical address. The logical cache is faster, but it needs to be flushed out and changed around more frequently. Another characterization is cache size, and because the performance of the cache is pretty sensitive to the nature of the workload, it's impossible to arrive at a single optimum cache size. So we want it to be small enough so that the overall cost per bit is close to that of main memory alone, but large enough so that the overall access time is close to that of the cache alone. So it's a kind of a balancing act, as most things in this field are. The larger the cache, the larger number of gates that we need to add on that chip, resulting in large caches being slightly slower than the small ones. The other thing is the area on the chip and the board will be limitations on the cache size. There are also mapping functions, and there are 3 different types of algorithms for mapping main memory into cache lines and determining which memory block currently occupies the cache line. And there are some examples in the text that are quite a bit detailed we'll go into, and there's a couple, I believe, in the associated homework assignment. So direct mapping, each block of main memory maps to one unique line in the cache. That's a fairly straightforward one. Associative, each block of main memory can map to any line in the cache. That one, the algorithm is a bit trickier to implement, but it allows us some different efficiencies. And then set associative, each block of main memory maps to one unique cache set. So direct mapping is the simplest technique. It maps each block of main memory into only one possible cache line. So the mapping is expressed as I is equal to J mod M. I is the cache line number, J is the main memory block number, and M is the lines in the cache. So we simply do a modulus, and so we would have, say 1000 and 1004 mapped into the first line of the cache if the modulus was indeed 4. If you reference words repeatedly, you go back and forth between 1000 and 1004, you will get some thrashing. The other thing is it's a fixed cache location for a given block. So here's an example of direct mapping. Each address has 3 different fields. There's the least significant bits identify a unique word or byte within the main memory block. The remaining bits specify one of the 2 S main blocks of main memory. And the cache logic interprets these S bits as a tag of S minus R bits and a line field of R bits. So here we would have the tag coming in from the main memory address, and then the data being transferred in. And again, the direct mapping is probably the simplest of the different approaches. Associative mapping is content addressable memory, or CAM, and allows each main memory block to be loaded into any line of the cache. The memory address is the tag plus the word, and it's designed such that when a bit string is supplied, the content addressable memory searches its entire memory in parallel for a match. If the content is found, the content addressable memory returns the address where the match is found, and some architectures also returns the associated data word. This process is pretty quick and only takes 1 clock cycle. The drawback to this is it requires a bit more complex circuitry in order to implement it, but it does give performance and a high degree of flexibility in things. So here the tag is 22 bits and the word is 2 bits. So we have very long tags and we have small words, and then we read in the tag and the data. And that avoids that modulus problem or thrashing back and forth in main memory. This is example 4.2 on page 139, and you'll definitely want to take a look at this to see how to do it. Set associative mapping is a compromise between that direct mapping and associative mapping. It exhibits the strengths of both direct and associative approaches and reduces their disadvantages. The cache consists of a number of sets. Each set contains a number of lines. Each word maps into multiple cache lines. So we don't have that thrashing, and uses a tag plus a set plus word paradigm. So you have three things: the tag, the set, and the word. And it can reduce to either direct mapping or associative mapping if you have very extreme cases in terms of how the memory is configured. So, here you see the tag and then the set and the word that corresponds to the data that gets mapped into the cache with the tag and the data mapped into it. And so you can map from multiple regions of the memory into the cache. The other thing is, once you have a filled cache, when you need to bring in a new block of the cache, which one of the existing blocks should you replace? For direct mapping, you only have one possible choice because you're doing the modulus, and so there's no choice possible. It makes it easy to come up with the replacement algorithms. But for associative and set associative techniques, you need a replacement algorithm. And to achieve high speed, you need to implement that in hardware. You can get lower speeds, obviously, with software, but you need to implement it in hardware really to get the higher speeds. So what are these replacement algorithms? Well, the most effective and probably the most common is least recently used. Replace the block in the set that has been in the cache longest with no reference to it. So, hey, I haven't looked at this in the longest time, I'm gonna replace it. And that's the most popular. First in, first out, replace the block in the set that's been in the cache the longest. That's easy to implement as round robin or using a circular buffer technique. In terms of algorithms, you learn that one in 151. Least frequently used is replace the block in the set that has experienced the fewest references. And that can be implemented by associating a counter with each line. Another characterization of caches is the write policy. So when a block is resident in a cache and needs to be replaced, there's two cases to consider. If we haven't done anything to it, then we can just overwrite it with a new block without writing the old block out to memory. But if there is a write operation that's been performed on that line, then we need to write that line out to main memory and then bring in the new data from the memory. There are two problems that we need to think about. One is there may be more than one device that has access to the main memory. And a more complex problem occurs when multiple processors are attached to the same bus and each has its own local cache. If words altered in one cache, it can conceivably invalidate words in other caches. And so there needs to be communication amongst those caches when you have multiple processors working. So in terms of write policy, the simplest technique is write through. All write operations are made to main memory as well as to the cache. The main disadvantage is it generates substantial memory traffic and it can create a bottleneck. Write back is another policy that memorizes the memory writes. They are made only in the cache, and portions of main memory get invalidated, and hence problems if you try to access those. So accesses by the I/O modules can be made only through the cache. Now that makes for complex circuitry, and because I/O is slow, a bit of a bottleneck, and we keep a dirty bit to indicate whether we did that. Another dimension of write policy is when a miss occurs at the cache level. One alternatives to this is the block containing the word to be fetched from main memory into the cache, and the processor proceeds with the write cycle, or no write allocate. The block containing the word to be written is modified in main memory and not loaded into the cache. We can also have problems with the bus. If more than one device has a cache and main memory is shared. If data in one cache is altered, this invalidates not only the corresponding word in main memory, but the same word in other caches. And even if you have a write through policy, the other caches may contain invalid data. A system that prevents this is said to maintain cache coherency. So one is bus watching with write through in order to get cache coherency. So all the caches are the same. And each cache controller monitors the address lines to detect write operations to memory by other bus masters. If another master writes to a location shared memory that also resides in that cache's memory, the cache controller invalidates the cache entry and says, hey, that's no good. You're going to have to pull it in again from main memory. This strategy depends on the use of the write through policy by all cache controllers. Hardware transparency, we have additional hardware to ensure that all updates to main memory via the cache are reflected in all caches. One processor modifies a word in its cache, this update is written to main memory. And the non-cacheable memory, only a portion of main memory is shared by more than one processor, so each processor gets its own portion of memory, and this is designated as non-cacheable. All accesses to shared memory are cache misses because the shared memory is never copied into a cache. And you can do this with chipset logic or high address bits to indicate the non-cacheable memory. Another design choice is line size. When a block of data is retrieved and placed in the cache, not only the desired words, but some number of adjacent words are retrieved. And as the block size increases from very small to larger, the hit ratio at first will increase because of the principle of locality. It later levels off. So, as the block size increases, you have more useful data that are brought into the cache. But as it gets bigger, the probability of using newly fetched information becomes less than the probability of reusing the information that has to be replaced. Larger blocks reduce the number of blocks that fit into cache, and as it becomes larger, each additional word is further from the requested word, and therefore less likely to be needed in the near future due to that principle of locality. Final consideration is the number of caches. It's become possible to have a cache on the same chip as the processor. In fact, a couple different levels. The on-chip cache reduces the processor's external bus activity and speeds up execution time. Do you still want off-chip cache? Yeah, definitely. And most contemporary designs include both on-chip and external caches, as we saw in the ARM architecture. So two-level cache is an internal cache designated as level 1 and an external one designated as level 2. And there's potential savings due to the use of an L2 cache, depends on the hit rates in both L1 and L2. The use of multi-level caches complements all the design issues, including size, replacement algorithm, and write policy. And L2 has little effect on the number of cache hits until it's twice the size of the L1. So that's also a consideration in terms of the design. And finally, unified or split cache. It's become desirable to split the cache, one dedicated to instructions and one dedicated to data. Both exist at the same level, typically as L1 caches. The unified has a higher hit rate and balances the load of instruction and data fetches automatically while maintaining only a single cache. Split cache eliminates the contention between the instruction fetch decode unit and the execution unit. And the trend in current design is to split the caches at L1 and have unified caches at higher levels such as L2 and L3. The following is Intel's cache evolution process, then when these things first appeared, as a bit of a history of the Intel chip. Thanks so much for watching.